Interplate and intraplate earthquakes. In this video, we explore one of the most fascinating and consequential aspects of earth science, the nature of earthquakes. More specifically, we will examine two major categories of earthquakes, interplate and intraplate earthquakes. Though both types involve the sudden release of energy within the Earth's crust, they arise from different geological circumstances, occur in different settings, and produce distinct patterns of seismic behavior. My goal today is not simply to define these terms, but to provide you with a deep, structured, and intuitive understanding of how they work, why they occur, and what they mean for human societies living on an ever-changing planet. Understanding Earth's dynamic structure. Before we explore interplate and intraplate earthquakes directly, it is essential to establish a foundation, how our planet is built and how it moves. Earth's outer shell, the lithosphere, is not a continuous, unbroken layer. Instead, it is divided into several massive pieces known as tectonic plates, rigid slabs of rock that float atop the softer, semi-fluid layer beneath called the asthenosphere. These plates are in constant motion. Some drift apart, others push together, still others slide laterally past one another. These motions occur at speeds measured in centimeters per year, about as fast as human fingernails grow. Though slow in human terms, this movement shapes continents, builds mountains, opens oceans, and, importantly for today's discussion, generates stress within the Earth's crust. When this accumulated stress exceeds the strength of the rocks break or slip, and the energy is released as seismic waves. What we experience on the surface is an earthquake. With this foundation, we turn now to interplate and intraplate earthquakes, two expressions of the same fundamental process, occurring under different geological contexts. Interplate earthquakes, when plates collide, separate, or slide. Interplate earthquakes are the most common and the most powerful type of earthquake on Earth. As their name suggests, they occur between tectonic plates, along their boundaries. Since tectonic plates are constantly moving relative to one another, stresses build up at the edges where plates interact. These boundaries are where Earth's crust is most dynamic, and consequently, where the majority of the world's seismic activity is concentrated. Let us look more closely at the three major types of plate boundaries and how earthquakes arise at each. A. 1. Convergent boundaries, plates colliding. At convergent boundaries, two plates move toward one another. Depending on the type of crust involved, continental or oceanic, the results differ. Subduction zones. If an oceanic plate meets a continental plate, the denser oceanic plate sinks beneath the lighter continental plate in a process called subduction. This is one of the most powerful earthquake-generating settings on Earth. The descending plate scrapes against the overriding plate, locking and sticking until a massive amount of stress accumulates. Eventually, the locked zone slips abruptly, producing a powerful interplate earthquake. Many of the strongest earthquakes in recorded history, such as the 2011 Tohoku earthquake in Japan and the 1960 Valdivia earthquake in Chile, occurred in subduction zones. Continental collision zones. When two continental plates converge, neither is dense enough to subduct completely. Instead, the crust crumples, buckles, and rises into towering mountain ranges. The Himalayas, for example, continue to grow today as the Indian plate pushes into the Eurasian plate. This collision also produces frequent interplate earthquakes, though generally not as deep or large as those along subduction zones. A. 2. Divergent boundaries, plates moving apart. Divergent boundaries occur when tectonic plates move away from each other. These boundaries are most commonly found along mid-ocean ridges, where new oceanic crust forms as magma rises from below the Earth's surface. Earthquakes at divergent boundaries tend to be shallower and less powerful compared to those at convergent boundaries, although they can still be significant. On continents, divergent boundaries can form rift valleys, such as the East African Rift. Here, Earthquakes occur as the crust stretches and fractures. A. 3. Transform boundaries, plates sliding past each other. At transform boundaries, plates move horizontally past one another. The most famous example is the San Andreas Fault in California, where the Pacific plate slides northward relative to the North American plate. These boundaries produce earthquakes when the plates lock along their edges and then suddenly slip. Earthquakes at transform boundaries can be shallow, frequent, and destructive because they occur close to the Earth's surface and often beneath densely populated regions. B. Characteristics of interplate earthquakes. To summarize, interplate earthquakes share several defining characteristics. They occur at plate boundaries, convergent, divergent, or transform. They constitute about 90% of all earthquakes worldwide. They include the largest and most destructive earthquakes ever recorded. They follow predictable patterns, because plate boundaries are well mapped. They often produce additional hazards, including tsunamis, volcanic eruptions, and landslides. Interplate earthquakes are the attention-grabbing giants of the seismic world. But they are not the only type, and in some ways, not even the most mysterious. 3. Intraplate earthquakes, shaking in the middle of stability. Now we turn to intraplate earthquakes, earthquakes that occur within a tectonic plate, far from the active boundaries where interplate earthquakes dominate. At first glance, this phenomenon may seem counterintuitive. If the most tectonic action takes place along the edges of plates, why would the interior of a plate, often thousands of kilometers from a boundary, experience seismic activity? Yet intraplate earthquakes do occur, and in some regions, they have caused significant damage and historical importance. To understand them, we must examine their geological causes and characteristics. A. Causes of intraplate earthquakes. Although their triggers are more diverse and often more subtle than interplate earthquakes, we can group their causes into several broad categories. 1. Ancient fault zones reactivating. Even though the interior of a plate appears stable from a short-term perspective, geologically speaking, it often contains ancient weaknesses created by long-forgotten tectonic events. Crustal features such as old rifts, fractures, or ancient collision zones may persist for millions or billions of years. Under certain conditions, these weaknesses can reactivate, producing earthquakes. For example, the New Madrid seismic zone in the central United States sits atop an ancient rift system. Although the region is far from any plate boundary today, it has experienced major earthquakes, notably the devastating events of 1811-1812. 2. Stresses transmitted across plates. Because tectonic plates are large, rigid structures, stresses generated at a plate boundary can travel long distances through the plate interior. In some cases, these stresses may accumulate at weak zones in the interior, triggering earthquakes far from the boundary. This mechanism helps explain why the interiors of continents, supposedly stable, can still experience moderate to significant earthquakes. 3. Mantle convection and hotspot activity. Some intraplate earthquakes occur near hotspots, areas where hot mantle material rises toward the surface, such as beneath Hawaii or Yellowstone. As magma moves upward, it generates stress in the surrounding rocks, potentially triggering earthquakes even in the absence of plate boundary interactions. 4. Human-induced causes. In modern times, human activity has become an increasingly important trigger for intraplate seismicity. Activities such as deep fluid injection, reservoir-induced seismicity from large dams, mining and quarrying, geothermal energy extraction, can alter the pressure conditions in the crust, reactivating faults that had been dormant. Although these earthquakes are typically smaller, some have caused notable damage, and their frequency has increased in regions where industrial activity affects underground pressures. B. Characteristics of intraplate earthquakes. Now that we understand their causes, let us briefly overview the features that distinguish intraplate earthquakes. They occur within tectonic plates, far from boundaries. They represent about 5 to 10% of global earthquakes, making them less common than interplate events. They often strike unexpectedly, because faults in plate interiors are less well mapped and understood. They can affect large areas, since seismic waves spread farther through older, colder, and more rigid continental crust. They may be linked to ancient geological structures, which can be difficult to detect with modern instruments. In many ways, the relative rarity and unpredictability of intraplate earthquakes make them a notable challenge for seismic hazard assessment. IV. Comparing interplate and intraplate earthquakes. Now that we have developed a clear understanding of both types of earthquakes, let us compare them directly. A. Location. Interplate earthquakes occur along plate boundaries. Intraplate earthquakes occur within the interior of plates. This single distinction is the fundamental difference between the two. B. Frequency. Interplate earthquakes are far more common, around 90% of all earthquakes. Intraplate earthquakes constitute only 5 to 10% of the total. C. Magnitude and impact. While interplate earthquakes produce the largest seismic events known, intraplate earthquakes can also be highly destructive. Interplate earthquakes are generally stronger because plate boundaries accumulate greater stress. Subduction zones in particular produce megathrust earthquakes exceeding magnitude 9. Intraplate earthquakes are less likely to reach these magnitudes, but they can feel more powerful over a wider area. This is because the interior of continental plates consist of older, denser, and more rigid rocks, which transmit seismic energy more efficiently. D. Predictability. Plate boundaries are well mapped, so interplate earthquakes are relatively predictable in terms of location. Intraplate earthquakes are far harder to anticipate because their faults are often hidden and inactive for long periods. This unpredictability poses challenges for urban planning and risk assessment. E. Associated hazards. Interplate earthquakes can generate tsunamis, volcanic eruptions, and extensive fault ruptures. Intraplate earthquakes typically do not generate tsunamis, except in rare cases when they occur beneath inland seas or reservoirs. Their primary hazard is strong, widespread ground shaking. V. Real-world examples. To further clarify the contrast, let us examine several real-world examples of each type of earthquake. A. Interplate earthquake examples. Japan, 2011 Tohoku earthquake. A magnitude 9.0 earthquake along the Japan Trench, a subduction zone. It generated a catastrophic tsunami and caused extensive damage. Chile, 1960 Valdivia earthquake. The largest earthquake ever recorded, at magnitude 9.5, occurred at a convergent boundary where the Nazca Plate subducts beneath South America. California, San Andreas Fault. Numerous significant earthquakes have occurred along this major transform boundary. B. Intraplate earthquake examples. New Madrid seismic zone, 1811-1812, USA. A series of powerful earthquakes estimated at around magnitude 7 to 8 occurred far from any plate boundary. They were felt as far away as New York City. Bhuj earthquake, 2001, India. A magnitude 7.7 earthquake struck the Indian plate interior, killing tens of thousands. Australian continental interior earthquakes. Australia experiences regular moderate earthquakes despite being located at the center of a tectonic plate. VI. Why understanding both types matters. Earthquake science is not merely academic. It has very real consequences for human life, infrastructure, and global development. Understanding both interplate and intraplate earthquakes is crucial for several reasons. A. Hazard assessment and risk reduction. Cities such as Tokyo, San Francisco, or Santiago face well-known risks from interplate seismicity. These regions have built robust monitoring systems and earthquake-resistant infrastructure. By contrast, regions like the U.S. Midwest or Central Australia have historically underestimated seismic risks. Because intraplate earthquakes are rare and unpredictable, they can catch populations unprepared. B. Tourism, industry, and nuclear safety. Critical facilities, such as nuclear power plants, dams, and oil refineries, require rigorous seismic hazard assessments. Misunderstanding the potential for intraplate earthquakes can lead to catastrophic miscalculations. C. Scientific insight into Earth's evolution. Studying intraplate earthquakes teaches us about Earth's ancient geological history, revealing how continents formed, broke apart, and reassembled over billions of years. Meanwhile, interplate earthquakes help us model plate motions and the forces that shape the Earth today. 7. Are these categories always distinct? An interesting question is whether interplate and intraplate earthquakes are always clearly separate. In reality, the distinction is mostly conceptual. Nature does not always fit human categories neatly. Some earthquakes occur in transitional zones, regions where the stresses from distant plate boundaries interact with ancient interior faults. The line between interplate and intraplate is sometimes blurred, and seismologists continue to refine their models. Nevertheless, the categories remain useful because they help organize our understanding and guide hazard planning. 8. The future of earthquake science. Earthquake science is advancing rapidly. New technologies, such as satellite-based GPS, machine learning models, and deep Earth imaging, enable scientists to map subtle crustal movements and detect hidden faults. We may never be able to predict the exact time and place of an earthquake, but our ability to identify risk zones is improving. As our understanding of both interplate and intraplate earthquakes deepens, so too does our capacity to build safer cities, more resilient infrastructure, and more informed societies. IX. Conclusion. Ladies and gentlemen, let us conclude by summarizing the key points of today's exploration. Interplate earthquakes occur at the boundaries of tectonic plates. They are common, powerful, and often catastrophic. They arise from direct interactions between plates, colliding, separating, or sliding past each other. Intraplate earthquakes occur within plate interiors. They are less common but can be widely felt and highly destructive. They arise from ancient faults, transmitted stresses, hotspot activity, or human actions. Both types of earthquakes remind us that the Earth is a living, evolving planet. Its crust may seem solid beneath our feet, but it is constantly moving, reshaping itself, and interacting through forces far larger than ourselves. Whether at the edges of tectonic plates or at their quiet centers, earthquakes reveal the restless energy at the heart of our world. In understanding these two types of earthquakes, interplate and intraplate, we not only gain scientific knowledge but also equip ourselves with the awareness needed to protect lives, build resilience, and respect the powerful natural systems that shape our existence.